The communication between the backend application and the database itself has always fascinated me, especially with their many protocols really custom built for this communication. I'm surprised that we didn't have standardized on an actual on-wire protocol for that. Yeah, we did standardize on the interfaces like ODBC and whatnot, but we never actually standardized on the communication protocol between the app and the database, right? I might be missing something, but as far as I know, there is no standard. Each vendor kind of create their own flavor of a binary protocol, fits their needs effectively. You know, your Mongo, MySQL, Postgres, they have their own custom on-wire protocol. Yeah, all of them are probably built on TCP, most definitely built on TCP. At the end of the day, that's the only thing you have on the network, right? UDP, TCP, and maybe some other things, but that's the ubiquitous protocol, right? But if you've been following this channel and this podcast, if you're listening for a while, you might have noticed me kind of advocating the use of a multiplexed based protocol. What does that mean? The communication between the backend application and database is kind of interesting. It's like a proxy almost, right? A reverse proxy of some sort. Why? Because as a client, as a user, you almost never actually send the query, right? The backend application does. You, where you live behind all these apps, you'll almost use a web app or a Python script or some sort of a, I don't know, Electron app that sends something to a web server often, and that web server turns around and send one or more query to the database to fulfill your request. So that's why you don't even need a database user behind that. It's all hidden, tucked in. That's why one of the best practices, like for backend application, to create a user that is so long, a database user that you get a persist on the backend has to be so long and random, and the password has to be super complex because no human is going to use it. Right? It's always going to be hopefully in a tucked in and not even saved anywhere. It's just probably in the process memory, loaded up in an environment variable or whatnot. But regardless, what you're going to notice is all these clients that they're going to talk to the backend eventually going to pull in all these requests. But all of them are talking to the same database eventually. Right? So even if you have 100,000 users, those 100,000 users coming from different connections, right? The backend to database connection is determined and well known. It's one backend most of the time talking to one database. Sure, you have replication and distributed databases, but that's most of the case. It's limited. And here where comes a concept called the connection pooling, which most of you listeners and followers of this channel know. The concept of connection pooling is it's pointless to have a connection for every single front-end user. That doesn't make any sense, right? What you want is to pool these connections so that even if these 1,000 web clients comes in, we don't really need 1,000 database connection. We can have 1 or 2 or 3 or 30, and then we multiplex, that's how you multiplex, right? Multiplex things into these fewer connections. Right? So you create a pool of connection and do the thing. And we can get into more details, but one of the most ubiquitous things that was discovered is this problem actually exists on the web today, right? Where we have this kind of multiplexity. Is that even a word? I don't know. Where a browser talking to one domain may send multiple concurrent requests to the same domain, you know? because of the mess we created that is called the web. Was CSS and JavaScript, 700 JavaScript files, and 300 bootstrap CSS, right? And so many other resources and JPEGs and images. So you find yourself sending a lot of requests to the same domain. So what do? It's the same problem. Right? The same problem always appear in life. It's almost like life. I'm going all over the place. It's almost like life is a pattern. Like these problems appear everywhere. Right? So you have these connections, like these requests, you multiplex them into one, right? Previously in HTTP 1.1, we didn't have that. We have to send one request per connection. And then we invented multiplexing, okay? Where we have HTTP 2. We can create one beautiful TCP connection, secure and all that stuff, and then multiplex all these requests into its own streams, like dedicated streams. And client created streams are odd numbers. So you have 1, 3, 7, and you can have server-side streams and do magic with that. So this concept kind of applies to the database. So it technically makes sense for the backend application to use a HTTP multiplex protocol such as HTTP 2 or 3, right? And use that on the backend. And that's what the topic of this video is. Right? And can we use HTTP 3 or HTTP 2 on the backend? Right? Planet Scale wrote up a blog article actually on January 4th. A beautiful article showing an experimental case where they used MySQL. They swept up their MySQL binary and replaced it with both HTTP 2 protocol and HTTP 3, and they show us the numbers. So this is what I'm going to go through. I'm going to go through this article and discuss and see the benefits of HTTP 3. How about we jump into it? All right. So this comes from planetscale.com. This comes from Matt Robinault, entitled Faster MySQL with HTTP 3. They do actually explain HTTP 2 and HTTP 3, and we're going to learn necessarily it's not really faster. There's areas where it's fast, and that's what we're going to focus on, right? So let's read the blurb here, the background, and then discuss. The background. As a part of our infrastructure initiative, we demanded new APIs and connectivity features for our database to support features that were not available on the MySQL protocol. We decided to stop bolting on a publicly accessible HTTP API. The API is not documented for public consumption just yet. It will be, I promise, but it is gRPC compatible. The HTTP interface led to the development of our serverless driver, PlanetScale Connect. In serverless compute context, your code is fundamentally not able to open a TCP socket and speak the MySQL binary protocol to us. The platforms require communication through HTTP, so it ended up being a nice fit. Oh, okay. So while they're talking about the serverless thing, for security reasons, serverless can't just open TCP. So they effectively, I think, restrictive to HTTP. So it ended up to being nice. All right. But can HTTP be faster than MySQL protocol? So you see, a lot of people actually might have considered using HTTP, but kind of shied from HTTP because of the concept of these headers, the extra headers that has nothing to do with databases. That's why database people don't use HTTP. But we always need to break into things and understand the benefits of using these protocols. Our new API aren't just gRPC. Specifically in our end, we use Connect Go, which is a gRPC compatible and gives us a lot of features. One of these features is the ability to potentially use HTTP 3 as a transport. HTTP 3 to me started making things very interesting. If you and me here, and I as the author, of course, not me, Hussein. If you're not familiar with HTTP 3, I suggest taking a detour of a bit of research, then back here, but just as the HTTP 3 is built on top of UDP rather than TCP, using the transport protocol called QUIC. We talked about HTTP3 in this channel. And if you're interested, go to my course, backend.husseinnasser.com. I go even in more details there. My theory was that the benefit of our new API start to yield tangible benefits. Let's see, what is the benefit? Okay, he talks about the setup here. We can skip this setup. It's just, we're not really interested in the setup. We know about the result. Right, so they configured 3 configurations. The first configuration is the native MySQL Binary Protocol client with TLS 1.2. I wish they made this a little bit more clear, but it's not. Okay? That's the first configuration, because you still need to secure the communication between backend and database, right? And MySQL does support that through TLS 1.2. Okay? You can do it through TLS 1.3, but it's a little more hectic. Right? HTTP client speaking HTTP 2. Right? I really appreciate the language being used here. Right? It's very clear and you know, concise. HTTP client speaking HTTP 3 through what they call the PSDP, which is their planet scale database, right? Plus HTTP 3, right? Let's go on and continue. We chose these because we wanted to see fundamentally if HTTP can compare to MySQL and if HTTP 3 yields any tangible benefits on top of HTTP 2. We're ignoring HTTP 1 since it's going to be objectively worse than both HTTP 2 and HTTP 3. I'm not sure about that. That's a statement. I don't know. It really depends what you're doing. You can't just assume it's worse, right? I mean, we've seen it with many backend application and articles of people actually moving away from HTTP 2 back to HTTP 1 because the resource consumption just shot high. Because what they don't discuss here is the cost of HTTP 2 and HTTP 3. They only discuss the benefits, but nobody discusses the cost of HTTP 2 and HTTP 3. There is a cost associated with it. And if you handle it, sure, take it. But if you can't, there is a lot of overhead to manage these puppies. There is almost zero overhead to manage this because it's HTTP 1 is native to TCP. It's literally text on TCP. Here, there are in-wire headers for HTTP 2, like the streams, the magic stuff, the magic numbers, and the headers, and the window sizes, and there is a lot of chattiness when it comes to HTTP 2 compared to vanilla HTTP 1, which is like really basic and simple. So I don't agree with that statement. This is okay. It's going to be objectively worse. You can't just make a statement like that, right? All right, so here are the tests. There. Connect plus select one. This is attempting to test the cold start. So what is cold start? To explain it, cold start is we don't have anything. I want to send a query, but in order to send a query, we need to initiate a connection, right? The setup cost to send a query, there is like hidden cost, and that's the cold start. The next time you start up, you want to send a query, the cold start have already done, you already started, you can send stuff on top of your query, right? On top of your connection, sorry. It establishes a connection to us and runs a select one using a new connection each run serially, right? So that's what they do. There's parallel. The test simply warms up a connection pool ahead of time, then runs select one in parallel, right? Medium select. The test reads 250 rows from a table with 2 columns, select star from medium. The total result size is approximately 50 kilobytes. Okay? So here they're probably testing the response, probably coming back. Insert, the test doing inverse of writing in the same database in bulk. So they're inserting a bulk insert. So what we're testing here effectively is the size of the request, whereas in the previous one, we're testing the size of the response. Right? Here, medium insert, we're testing, because the insert time is going to be massive. So compressing that is really valuable, right? Compressing becomes really valuable here. Large select, this test reads 100,000 rows, so 27 megs coming back, right? So the query is tiny, I mean the size of the actual request, but what comes back is large, right? So let's look at the results, right? For those listening, we're looking at the connect plus select. So each protocol is tested against a connect. So that means creating a connection, encrypting the connection, right? That's the TLS session, and then sending the select one, which is a very simple query. Okay? And we're all testing the latency here. So it took MySQL native binary protocol with TLS 1.2, and again, I really wish they actually spelled that out. Right? It took MySQL around 175 milliseconds, right? While their PSD-DB on HTTP2, it took it 50 milliseconds only, while the HTTP3 is also 50 milliseconds, really identical. So 50 milliseconds versus 175. So you have 100 milliseconds there. And the saving is the cost is really just the connection itself. So the connection establishment, which we know it's all TCP, right? Except for HTTP3, which is quick, which is UDP. Still, there is a connection establishment. But the cost really goes into this because TLS 1.2 is 2 round trips, right? You have to first kind of flirt in TLS 1.2. It says, hey, I support this and I support all these key exchange algorithm, I support these ciphers, let's pick for me, server. And then the server says, okay, pick this, I pick the Diffie-Hellman, I pick this, and then we go ahead and actually do the connection. Whereas TLS 1.3 says, hey, you don't get a choice. I'm going to assume something, let's always communicate in key exchange, and this is the Diffie-Hellman, and here's my parameters, just go ahead and do it, right? And then the server will pick the cipher, which is the symmetric key cipher, not the key exchange. The key exchange is already determined, right? And then we'll pick the cipher, and then we'll tell the client, hey, I picked that cipher, and here's my parameter, let's complete. By this time, server already has this session key. Yeah? So that's why TLS 1.3 is way faster than 50% faster, actually, than TLS 1.2. And that's exactly what we're seeing with MySQL. So nothing about MySQL is bad so far. MySQL is okay. Right? It's just, I would really love to see the same graph with MySQL and TLS 1.3 and see if there is benefits for connection establishment. That's it. Right? If MySQL binary can be built on top of TLS 1.3 or can be used with TLS 1.3, that's fine. Let's read the highlights, which is, I think they might mention some of this stuff. From my laptop, I expected a major improvement, but the minimum went from 162 to 35-ish millisecond, so 35, not 50, over HTTP, while the max also stayed steady for HTTP and jumps up quite a bit for MySQL. I suspect the biggest one here is fundamentally because of the TLS. Okay, we kind of agree here. Because of the difference of TLS. Both HTTP and TLS require HTTP 1.3. Both HTTP2 and HTTP3 require TLS 1.3, another false statement. No, they do not. HTTP2 do not require TLS 1.3. HTTP3 is built on TLS 1.3. You don't have an option. HTTP3 is built on Quick. Quick is kind of merged with the connection setup as TLS 1.3. So you do the SYN and you also establish the TLS 1.3 connection in one thing. The Quick setup is really one round trip. It is the TLS 1.3. HTTP2 is built on TCP, right? And the TLS is kind of disconnected from the TCP. So definitely, of course, you can have TLS 1.2 on top of HTTP. So that's a wrong statement, right? So that's another thing. So I bet if you use HTTP2 with TLS 1.2, then you're going to see a similar bump in latency in a negative way with PSD-DB HTTP2, because that will just be slower, right? And of course, the TLS 1.3 also supports 0 RTT if you have a already established a session and that you can have a pre-share key extension, TLS extension, that will allow you to kind of encrypt your data and reestablish the session, right? Get a brand new session key effectively, and then go ahead and continue the encryption, right? And the server can recreate this new session key just like that very quickly, right? On the same breath. So no round trip is required, right? Well, at TLS 1.3 by default is one round trip. So you have to send and wait for the server to respond, so you can actually send the encrypted zero RTT with the same breath. If you have communicated before, you can do that. So it's really powerful stuff. While in theory, MySQL clients could also support TLS 1.3. TLS support in clients is typically not great. I have to agree. Right? It's very slow to roll, older libraries with newer features like TLS 1.3. So in this case, negotiated with TLS 1.2. So they did mention this, right? I wish it's spelled out in the graph, right? So MySQL should be like between parentheses TLS 1.2, right? This saves a full round trip when establishing a new connection. Right? So what was surprising to me, I expected this to only reflected on high latency network and geographic distances, but this was surprising better on our EC2 instance on US West, from 11 millisecond down to 3 to 4 milliseconds. Right? Okay. Overall, it's very clear that both HTTP 2 and 3 are substantially better for cold start. Again, can't just say that. You gotta try MySQL on TLS 1.3 to, if that is true, then you will, because at this point it's just connection, has nothing to do with HTTP technically, right? We were testing connection establishment, right? So if you do the same thing with MySQL on top of TLS 1.3, which is most of the cost, then you should see the similar time, you should see very similar latencies effectively, right? So you can't just say that, oh, HTTP 3.2 is better. While these results all look relatively similar, to me, that's a good thing. We can see some improvement. Now they're doing the parallel select, which kind of proves the point here. The parallel select one, all the numbers are similar. Why? The numbers are similar because the connections is what took time. The rest of the stuff doesn't really buy you anything. You know where this will actually be beneficial to actually see numbers, which I don't think it exists, is in a high concurrent environment, which no test actually does that. You should have like 1,000 or 20,000 requests pulled into fewer connections. Try sending concurrently or start multiple transactions. I don't know, off the cuff, like 3,000 transactions concurrently from the backend application to the database, and let each of the transactions send a lot of queries. Test that on HTTP 2, and MySQL, right? For MySQL, you'll have to establish many connections because I don't think they support pipelining. And Postgres really started to support pipelining recently. But pipelining, it always gets you like very weird results, You got to make sure that if you send multiple requests one after the other on the same connection, they better be executed in the same order, and then give you back the results. But yeah, that will be a fantastic test, and that same test will really measure. Now that's the second test. What will be nice to see is the database server cost, right, and the backend as well, CPU wise, and not much memory, but CPU is most important. Because, and here's the thing, and the rest of the stuff doesn't really matter. We don't need to go through it. That's basically the summary what we have. So let's go through this. What we need to see is the cost of HTTP2 and HTTP3 mainly comes back is to parsing. What does that mean? To understand that, we need to understand how networking works, right? And I don't think we need the screen anymore. So a very well-written article, there are a lot of details here, which we have more. Of course, everything can be improved. It's a experimental at the end of the day. They actually did mention great work from the Planet Scale team. Matt, great job. I apologize, I might be a little bit harsh in some posts. Just take it as just a criticism. You can leave it or take it. That's fine. But very well written. Absolutely love it. We never seen anything like this before. HTTP3, using HTTP3 on a database. So you guys are pushing the boundary, and this is what we need in the realm of database and backend engineering. So kudos, great work, you guys. I know the work that have been I know the work that must have been took, to actually replace the client libraries so that it supports HTTP3 and HTTP2 and collect these numbers and run all these tests, right? So fantastic work. Keep up the good work. And with that said, let's go and continue the discussion on why HTTP2 and HTTP3 is costlier. So in order to understand that, right, the benefits of HTTP2 and HTTP3 is really, to me, is the multiplexing nature. Yeah? We have one backend application sending many clients. That's the number one benefit here, right? And that's why proxies like Envoy use HTTP2 on their backend. That's why gRPC use HTTP2. The beauty of having to control the low-level stream, having the multiplexing feature is really powerful. So we have established the connection once, and I can send many requests on the same connection. That's the power here. But we gotta understand that at the end of the day, these requests, right, sending 1,000 query on a single connection, will transmit into each of these query will be their own HTTP2 or HTTP3. I think they call it datagram, And then these guys have their own headers. So HTTP2 have their own headers. It says, oh, this is the stream ID. This is, I don't know what. This is the window size. This is like in the case of HTTP3, there's the connection ID. So there is so much, overhead to tagging these things. So each query that you send, yeah, sure, is going to be compressed, HTTP speak, and will be binary, but there is headers added. But at the end of the day, they will, in the network, they either fill on top of TCP, which is HTTP2, or UDP, which is HTTP3. So today, in the Linux and Windows kernel, these protocols are not understood at the kernel level. The kernel knows UDP, and the kernel knows TCP. And it's going to do work for you in that layer. So if you send these queries, will end up into TCP segments, and they're going to be carried into a bunch of TCP segments with the destination port, destination IP, source port, source IP. That's it at the end of the day. Yeah, these stream of segments will be encrypted by higher layers. And that's it. So what happens is these stream of TCP segments will arrive in the NIC, the network controller, the network interface controller, will be buffered, coalesced in some cases, some network card. And then this will trigger an interrupt, right, to the CPU or the DMA, the direct memory access in the motherboard and all this stuff, to trigger, says, hey, I want to transfer now this, please transfer this amount of segments that I just received to you, kernel. So the kernel will do, that will instruct that to move from the buffer, from the NIC. This data is just, at this point, is just encrypted bytes, right? They go from the NIC to the kernel memory. Still, the backend not even close to see any of this HTTP or 3 or 2 data. Now the kernel will look at this and says, okay, which process actually ask for this? Well, it's going to port this. Oh, so it's this actually, this file descriptor, this socket. So let me copy this data into that particular buffer. So start copying this data into the buffer. And now it's up to the kernel doesn't even decrypt or do anything, right? It's just to the kernel, it's just data that arrived. Now the backend application is responsible to call a function called read to actually read the data from the kernel into its own process virtual memory, right? That's what will happen. So now we're going to move the data from the kernel. And what's this data? This, again, it's an encrypted byte. We have no clue about streams. We have no clue about query. We have no clue about anything. So this data is copied into the process memory, which is now your backend application or the database server application, MySQL in this case, will need to actually understand how to take these encrypted segments. First of all, because now we're layer 4, right? We go up one layer, layer 5, right? Session layer. And then we'll start decrypting, which is TLS will take care of this. So okay, which session key we used? Okay, this session key we used for this particular connection, do the mapping. And now we'll start decrypting. That's a cost, right? The cost of decrypting the content. Now we have a bunch of unencrypted stuff in my process memory, and even that will involve some copying, and we're going to involve the CPU in the process, right? So now we have unencrypted data, but still the job is not done. If this was HTTP 1, the job is done, because that segment is the data. That's it, because HTTP 1 is a simple text, okay? And then we can just group a bunch of unencrypted segments, right? And that becomes, oh, here's where the start of the request, here's the end of the request. Right? Binary, I have no idea how the MySQL binary looks like, but it would be something similar. They will start parsing. In HTTP 2 and HTTP 3, the job is not even close to done. And again, who's doing this work? Is the backend application and the database if it supports HTTP 2 or HTTP 3, right? Now, with HTTP 2, now you have to start assembling this unencrypted data and then look for, not requests, you look for streams now. So stream 1 is, oh, this header is now stream 1, this is stream 2, this is stream 5, this is stream 7, and then start parsing to find the streams. And then once you find the streams, you find requests within streams, and this is another kind of parsing, right? And that additional overhead is why HTTP 2 and HTTP 3, right, cost more CPU and slightly more RAM compared to native, simpler protocol. If you add something, there's always cost to it. And that's what the Lucid chart, I mean, a few years back, they found out this problem right away. They enable HTTP 2 blindly, and all of a sudden their backend application CPU is just shot really high to 90 to 100%, right? Because of the load of this additional thing they are using. Right? And of course, there is a lot of progress from the community, from the Quick community and the HTTP2 community to improve the cost of parsing. I call it parsing. Maybe there is another word the community would like to use, but to me, it's just parsing. You're parsing the protocol to find out the actual content, right? But this could get better and better, of course, but that's the cost associated with using HTTP 3 and HTTP 2. If you have unlimited CPU and RAM, knock yourself out, use HTTP 2 and HTTP 3. Just understand the cost. If you really, HTTP 1 is not that bad, really. The only badness, if you want to call it bad, is the lack of multiplexing. If you want to send a lot of requests in the same connection, you gotta wait for the response to come back for the previous request before you send another request. There have been, improvement on the idea of pipelining, where you can send multiple requests without waiting for a response. But then there must be a kind of symbiotic relationship between the client and the server to guarantee the order of things that come back. If I send request number 1, request number 2, request number 3, what if request number 1 takes longer than request number 2? So the server can process request number 2, right? And might respond before, right? If it responds before, then the whole thing just breaks apart, because now you got request number 2 before request number 1, and you have no idea, is this the response for the first request or the second? You have no clue, right? Unless you built it in the protocol itself, such that you tag the response with the request. You can absolutely do that in the application itself, okay? And you can build something like that. But again, there are problems with, of course, HTTP2, TCP, head of line blocking, and things like that. But again, I absolutely enjoy. When I saw this on Twitter, I really enjoyed it. I thought, you know what, let's make a quick video about this. Again, great work on this, and I think there is a potential for this. I just need to. I still think we need to understand the ramification of this. You know, the cost. The cost has to be highlighted to using these new protocols. That's it for me today. Hope you enjoyed this video. What do you guys think about this? Let me know. Call me out if anything I said. And again, thanks for PlanetScale. Great articles. I'd love to see more of these beautiful articles. Really good job. Thank you so much.